Today we're going to be talking about reducing agents and oxidizing agents and how strong they are, which one I'm going to use to try to get a reaction to run. And so as we're going through this, I would recommend that you have your standard reduction potential table, which is on the inside back cover of your book. I'd recommend that you have that open so that you can find these reactions as I'm talking about them. Okay, so you already know that if I want to find a reduction potential, that is what the table is. They are reduction potentials. If you look at all those reactions in there, they are reduction reactions. And so you're going to look at them just exactly the way they are. So to find a reduction potential, you're going to find the species on the left side of the reaction, and you're going to take the value just as it is, okay? Then if you want to find an oxidation potential, we did this in the last chapter where if you have to take the reaction and flip it around because it's actually being oxidized, you have to find the species on the right side and take its opposite value. So this is what you've already learned, okay? So when I look at the table, down here at the bottom right-hand side, our reduction potential is very, very high. The reverse reaction is when things are being oxidized. So the reverse reaction is when it is oxidized. Now, if you recall, something that is reduced is an oxidizing agent. So because the reduction potential on the bottom right-hand side of these things is very, very high, that's going to make them very powerful oxidizing agents. On the other hand, if I flip my reaction backwards, because the reverse reaction is oxidized, when I flip these numbers backwards, they're going to become positive, and that means everything in the upper left is going to be a very powerful reducing agent once the reaction is flipped around. So if I want to find a strong oxidizing agent, I'm going to look for the species on the left side of the reaction, and the further down on the right, the stronger a reducing agent, the stronger an oxidizing agent it is, because all of these things are being reduced. If I want to find a reducing agent, I have to look at the oxidation side of things. So I would have to flip all the equations backwards. To find a strong reducing agent, I'm going to look for the species on the right side of the equation, and the farther up and on the left it is, that's going to be your really strong reducing agents. And reducing and right both start with an R, if that helps you at all. Okay, so let's try to work a couple of problems here to see if we can make this make some sense. All right, so example 10.6 is asking us to find the strongest reducing agents. So I want a reducing agent, and the choices it gives me are zinc, gold, calcium, manganese, or lead, okay? So if I want a strong reducing agent, that means that that element has to be oxidized. So if I want it to be oxidized, all of those equations have to be flipped backwards, and all of the values have to be flipped so that if they're positive, you make them negative. In place of negative, you're going to make them positive. So that has to be flipped as well. So we're looking for a strong reducing agent. So we're looking for something that's going to be up here. The reverse reaction is going to be as high as possible on this side. Now, he threw you a zinger when he gave you this zinc, because if you look at your table, there are some reactions where you can find certain species on both sides in different parts of the table. But zinc is only on the table as an element that can be reduced, going from zinc with a positive 2 charge to just atomic zinc. You can't find any place on the table where you can flip it around and have zinc be a reactant. It's only on the left-hand side. There isn't any place where I can find zinc on the right-hand side of the reactions that are listed on the table. So that means if I can't find it on the right-hand side of the reaction, that means that zinc can't be reduced at all. It can't be oxidized at all. And so therefore, that means it's not going to be a powerful reduction agent. And so I can't use that one at all. Okay, now if you look for gold, can you find gold on the table? again, you need to find it on, you need to find gold on the right-hand side of the reaction, and you'll find it down on the, it's about right here on the table. And so I have to take that reaction, I have to flip it backwards so that the gold is a reactant. And so when I take that and flip it backwards, that gives me a value of a negative 1.50. Okay, if I look for calcium, calcium is up in this part of the table. It's on the right-hand side. I need to flip it around so that the calcium is being oxidized because I'm looking for a reducing agent. And so when I flip that number backwards, I have a 2.87. Okay, manganese, same thing. You see manganese on the table? You need to find it on the right-hand side, and then you'll need to flip the equation backwards and also flip the value backwards. And so this is going to be a 1.18. And then lead, again, find it on the right-hand side of the equation, but because I am looking for a reducing agent, it has to be oxidized, so I got to flip it backwards, and that's going to give me a 0.126. So did you find all of those on the table? Once you found them, you got to flip them backwards. Remember, this is the one you have to be careful about, though, because this wasn't ever on the right side of the equation so that I could flip it backwards to begin with. It was only on the left to start with. They're reducing agents. I'm looking for a reducing agent, so I have to have an oxidation reaction. This is standard reduction potential. So if I'm looking for an oxidation reaction, I got to flip them all backwards, and it won't go if this can't be on the left-hand side of the equation, okay? So when I look at all these numbers, this calcium then has the highest number, and so it is going to be the best reduction agent that they gave you. Another way to look at it is to say, if I want a strong reducing agent, I'm going to look for the species on the right side of the reaction, and the farthest up on the left, the stronger it is. And you can find, if I look on the right side of the reaction, the calcium is as far up and on the left as any of these are, okay? All right, so now let's look at example 10.7. And this is where all of this comes into being super useful in chemistry, because sometimes you need to run a reaction and you have to figure out which one of these is gonna be the best choice. So example 10.7 says a chemist wants to turn platinum into platinum 2+. So example 10.7, we want to do this. Okay, I want to do that, and I want to know which one of these is going to be the best to use, whether it's going to be permanganate, whether I'm going to use iodine, or whether I'm going to use lead. Lead 2+. Makes a difference, doesn't it? Okay, so the first thing I need to do is I need to find this reaction on the table. So platinum, obviously that is backwards of everything that's written on the table because he's wanting to oxidize it. So you've got to take the reactions and flip them backwards. So you'll find that equation on the, it's about 2/3 of the way down on the right-hand side. It has a 1.20. And so since I flipped this backwards, this reaction is going to have a negative 1.20. So this is being oxidized, and so therefore I need a strong oxidizing agent, a powerful oxidizing agent. If I'm looking for an oxidizing agent, I have to have something that's going to be reduced. So that means that when I look for these, I'm going to look for them exactly as they already are on the table. So if you look at permanganate, MnO4-, you can see that again and it's almost all the way down on the bottom on the right side. We need that to be on the left-hand side because we want it to be reduced because we're going to power an oxidation reaction. And so that has a potential of 1.51. The iodine, if you look at it, It is, I believe it's also on the right-hand side. Yeah, about a third of the way down on the right-hand side. And you can see that that has a potential of 0.5355. And then the lead with a positive 2 is going to have a negative 0.126. Okay. So which one of these is going to be the best one to use? Well, if I add these two together, I end up with a negative number. That's not going to help me at all because the reaction won't go at all, because if it's got a negative number, so that won't work. So this one won't work. If I add these two potentials together, I'm still going to end up with a negative number. So that means this one won't work either. This is the only one with the potential high enough to overcome this negative. And so that means this is going to be my best choice for a substance in order to run this reaction here. Okay? Then the second part of the equation, or second part of the problem, says a chemist wants to reduce chromium 3 plus to chromium. So we're wanting to do this. We're wanting to do this, and I have 3 choices. I could use platinum, I could use manganese, or I could use nickel. So once again, I need to look at the table to find out exactly what it is I'm dealing with. I need to, when I find the chromium on here, see where that is. There it is, about halfway down on the left-hand side. That reaction has a negative 0.74. So again, this is not something, it's not a reaction that wants to occur easily. So I've got to have something to force the reaction so that I will end up with a positive number. If I look, that means that since this reaction was in the table this way, I have to take these and use it in the reverse, okay? And so I am looking, since this is being reduced, I want a strong oxidizing agent. So to find an oxidizing agent, I have to look for the species on the left side. So if I look at the nickel, I'm going to have a 0.250. And let's see where that was on there just so I can help you find it. On the left-hand side, most of the way down. The nickel is on the right-hand side of the equation. I have to flip it backwards. And so I have to find all of these on the right-hand side of the equation. Okay. The manganese, if you look for that one, you should find that that's a 1.18. And then the platinum, again, this is one of those where I have a problem because the platinum, I can't find that on the right-hand side of the equation anywhere. The only place you find the platinum is, again, about 2/3 of the way down on the right-hand side. And I can't take platinum and make it go the other direction because then this won't be a reactant. It's going to be a product, and this has to be a reactant in order to make it work. So this one isn't even a possibility at all. This one has a potential that's too low in order to overcome the negative of this one. So that means that my manganese is going to become my only choice to make that reaction run, okay? Now, again, this can be confusing because you're constantly having to think back and forth as to, okay, this reaction's running forward, so I have to run this reaction backward. Hang in there, do some practice, and I have a lot of confidence in you that you will be able to get it.